Welcome to a session on black body radiation. This is the very first topic under quantum mechanics, which belongs to unit number 1. You may have immediate question, why should I learn quantum mechanics? Because I already learned classical mechanics or Newtonian mechanics in lower classes. First of all, understand the limitations of classical mechanics. Classical mechanics or Newtonian mechanics can explain macroscopic phenomena only, which means classical mechanics deals with larger objects. For example, motion of a cricket ball, motion of an aeroplane, motion of planets, motion of sun around the galaxies. But when we consider the motion of microparticles such as electrons, protons, classical mechanics fails. For example, black body radiation, photoelectric effect, Compton effect cannot be explained on the basis of classical mechanics. So, a new type of mechanics is introduced to explain these facts or phenomena. That is called as quantum mechanics. So, final conclusion is classical mechanics can explain macroscopic phenomena. Quantum mechanics can explain microscopic phenomena. Our topic of interest is black body radiation for this session. First of all, understand what is a black body. A body that completely absorbs radiation of all wavelengths incident on it is referred as a black body. For example, let us consider this body. When radiation is incident inside, then if this radiation got completely absorbed by this body is called as black body. When such body is heated, it emits radiations called black body radiations. If you heat this body, it can emit the radiations also. So a perfect black body is a good absorber as well as good emitter of all the wavelengths of radiations. In actual practice, there is no body as a perfect black body, but lamp black may be regarded as a black body because it is able to absorb nearly 99% of the instant radiations. Scientist Ferri suggested a black body which consists of a hollow thick-walled sphere either made up of with iron or copper, painted lamp black internally and provided a small opening to enter the radiation. If you observe this figure, it is made this particular sphere is made up of with iron or copper. Internally it is coated with lamp black. When any radiation falls on this opening, it enters the cavity, gets reflected by the sphere and gets absorbed. Here you observe a radiation is incidenting and it is passing through this opening, and immediately at first it strikes at this place, then reflects to this place, then it reflects to this place, it reflects to this place, and so on. So these are called as multiple reflections. This radiation suffers multiple reflections. At each and every reflection, certain amount of radiation got absorbed. If this body completely absorbs the instant radiation, then it is called as a black body. If we heat the cavity at various temperatures, it will emit radiations of all the wavelengths. Lummer and Prinsham investigated the distribution of energy among the different wavelengths in thermal spectrum of black body radiation. So what they did is simply they heated this black body to various temperatures. To various temperatures. For example, uh, they heated to 3000 Kelvin, 4000 Kelvin, 5000 Kelvin, 6000 Kelvin. Then they plotted a graph between wavelength and intensity by taking wavelength along the x-axis and intensity along the y-axis. This graph is called as black body radiation spectrum. So let us observe what are the conclusions from the black body radiation spectrum observed by the Lummer and Prinsham. The first conclusion is at a given temperature, the energy is not uniformly distributed in the radiation spectrum of the black body. Conclusion number 2 is at a given temperature, the intensity of radiation increases with the increase in wavelength, and at a particular wavelength, its value is maximum. With further increase in wavelength, the intensity of radiation decreases. For example, when the black body is heated to T equal to 6000 Kelvin, if you clearly observe, as wavelength increases along x-axis, there is a corresponding rise in the intensity along the y-axis. At a particular wavelength, for example, in this case, at 600 angstroms, the intensity becomes maximum. This particular wavelength is called as lambda max. So beyond this lambda max, there is a corresponding decrement in intensity, even though wavelength increases. Conclusion number 3 is, with increasing temperature, lambda max decreases. Yes, at T equal to 3000 Kelvin, this is the lambda max value, approximately 1200 angstroms. At T equal to 4000 Kelvin, the lambda max shifted to 700 angstroms. At T equal to 6000 K, the lambda max shifted to 600 angstroms. As temperature increases, intensity also increases corresponding to all wavelengths. You can observe at T equal to 3000 K, this is the highest intensity. At T equal to 6000 K, this is the highest intensity, which concludes that as temperature increases, there is a corresponding rise in intensity also. The area under each spectrum represents the total energy emitted at that particular temperature, which means that, for example, if you take these two curves, this curve is drawn between wavelength and intensity at T equal to 5000 Kelvin. This curve is drawn at T equal to 6000 Kelvin. So this curve occupies less area and this curve occupies more area, which means that more area means the black body emitting more amount of energy. Less area under the curve means less amount of energy is emitting by black body. And it is also observed that the area is directly proportional to the fourth power of the temperature of the black body. So the area occupied is directly proportional to the fourth power of temperature of the black body. So this also you can observe from the graph. As temperature is very, very less, the area occupied is also very, very less. As temperature is very, very high at 6000 Kelvin, it occupies more area. The relation, the mathematical relation between these two is area is directly proportional to T to the power of 4. Let us see some of the applications of the black body radiation. There are two main applications. One is we can calculate the temperature of the distant cosmic bodies. The second one is thermal vision. Let us see this picture. Yes, this is the picture of universe. In this, you can find different stars with different colors. For example, these stars are red stars, and these stars are blue stars, and these stars are red stars, yellow stars, green stars. So, how can we find out the temperatures of the stars? For example, if the star is appearing in red color, its temperature is approximately 4000 Kelvin. If the star is appearing in yellow color, its temperature is approximately 6000 Kelvin. If the star is appearing in blue, then its temperature is around 18,000 Kelvin. The next application is thermal imaging. You can see this is a thermal image of a male person. You can observe different colors on his face. His hair is in blue color, which means that the hair temperature is around 29 degrees centigrade. You can see at this part there is a red color. So red color indicating that the temperature is around 35 to 36 degrees centigrade. So you can see some green portions on his face. So this indicates that at that particular place, the temperature is around 31.5 degrees centigrade to 32 degrees centigrade. So these are the some applications of the black body radiation.